What role do Kirchhoff's laws play in complex circuits? Imagine trying to solve a puzzle where all the pieces are connected in many different ways. That's what analyzing complex electrical circuits can feel like. Here is where Kirchhoff's laws come into play. They are like the rules of the game that help us figure out how current and voltage behave in these tricky setups. These laws are essential tools in electrical engineering because they let us analyze circuits that are too complicated for simple series or parallel calculations. When circuits have multiple loops and junctions, Kirchhoff's laws give us a systematic way to write equations that describe the current flowing through each part and the voltage across each component. Kirchhoff's first law, also called the current law, states that the total current entering any junction or node in a circuit must equal the total current leaving that junction. This is based on the principle of conservation of electric charge. It means that no current is lost or gained at a connection point. So, if three wires meet at a junction, the sum of the currents flowing into the junction must be the same as the sum flowing out. This law helps us understand how current splits or combines at different points in a circuit. Kirchhoff's second law, known as the voltage law, says that the sum of all voltage changes around any closed loop in a circuit must equal zero. This is because energy is conserved as charges move around the loop. When a charge moves through a resistor, it loses voltage, but when it passes through a power source like a battery, it gains voltage. Adding up all these voltage rises and drops around a loop must balance out to zero. This law helps us find the voltage across each component in a circuit with multiple loops. In complex circuits, these laws are used together to create a set of equations. For example, at each junction, Kirchhoff's current law helps us write equations for how currents split or join. For each loop, Kirchhoff's voltage law helps us write equations for the voltage drops and rises. These equations are often numerous and interconnected, especially in circuits with many loops and nodes. By solving these simultaneous equations, engineers can find the unknown currents and voltages in the circuit. Kirchhoff's laws are especially useful when circuits contain different types of components like resistors, capacitors, and inductors arranged in complex ways. They allow us to analyze how current flows through each part and how voltage is distributed across the entire network. Techniques like mesh analysis and node analysis relying heavily on these laws to systematically solve circuits. They also help in transient analysis, where we look at how voltages and currents change over time during switching or dynamic conditions. These laws are fundamental for designing and troubleshooting electrical systems, from power grids to electronic devices. Although they assume ideal conditions, like steady currents and no changing magnetic fields, they are still very accurate for most practical circuit analysis. Without Kirchhoff's laws, understanding how complex circuits work would be nearly impossible. They give us the rules to predict and control electrical behavior, making them the backbone of circuit theory in electrical engineering.